In this video, we will be looking at some characteristics of functions that we haven't looked at in the past. And we're going to start with something about inverse. Now we have function f at x, and we want to determine the inverse of f at x in both scenarios. So that means we're going to have to start off by switching our x and y. So x equals 4y plus 1 all over 2. And now let's isolate for y. I'm just going to do a little bit of cross multiplication here. So 2 times x equals 1 times 4y plus 1. And now if I need to isolate for y, I will bring the 1 over and then divide by 4 or multiply by a quarter, whichever you prefer. I'll just divide by 4 this time. And there we are. There's our inverse. Now with this inverse, let's see what we need to find next. We need to find f of the inverse. So we're doing a composite function. So inside function f, we're going to put the inverse. And the inverse was 2x minus 1 over 4. Okay, so I need to put this in for x for the original function. As a reminder, the original function is 4x plus 1 all over 2. So I'm going to write 4, and then I'll put my inverse for what the original x was, and then plus 1 all over 2. And now we just need to clean this up. Lucky for us, these 4's cancel out nicely. So our numerator now is just 2x minus 1 plus 1 all over 2. Negative 1 plus 1 is 0. So we have 2x over 2, which is just a nice little x. So that's our first example. When I put the inverse of a function back into its original self, I got an x. Let's see what happens if we try it for another function. We have f at x equals 2x over 5 minus 3. So I'll start off with my swap. And now I'll start isolating. So I'll bring that 3 over. So we have x plus 3. I want to get rid of that 5, so I can either cross multiply or just multiply by 5. They're going to do the same thing. So that's going to be 5x plus 15 equals 2y, and then we can divide by 2. So here is the inverse of my second function. And this time, we're going to start with the inverse. That's going to be our outside function, and we're going to put the original function in. The original function was 2x over 5 minus 3. So that's going to go in for x in the inverse. So I'm going to have 5, but then instead of x, I'm going to put 2x over 5 minus 3, and then add 15, and then all over 2. So let's go ahead and distribute that 5 in. That's going to be 10x over 5, which is 2x. 5 times negative 3 is 15. Then on the outside, we had plus 15 over 2. The negative 15 plus 15 is 0, so that we have 2x over 2, which is x once again. So even though we had a different function, when I put the inverse back into its original, or the original into its inverse, we ended up with x. So what can we conclude? We can conclude that if we take the composite of function f composite its inverse, you're going to get x. Or if you take the composite of an inverse with its original, you also get x. All right. Now let's look at some characteristics related to even and odd functions. So we have a set of polynomial functions, set A and set B. We're going to graph or sketch these functions just using Desmos to be quick and efficient here. So first we have a parabola. Roughly it looks like this, starting at 4 for its vertex. The next one is quartic, and if you go to Desmos, you'll have something like this, going through -2 and 2 and 0 as the x-intercepts. X to the 4 minus 4 will look something like this at -4. 5x to the 4 plus 4x squared minus 4 looks something like this. And finally, f at x equals 4 just looks something like this. Now if you look at all of these functions, they all have even symmetry. They're all even functions here. So what we're going to do for this investigation is pick two functions from set A, whatever two you want, and add them to create a new function. You'll do it algebraically and you'll do it graphically. And again, we can just use Desmos for this investigation just to get the characteristic. So I'll do one here and you can do a few more to see what happens. So I'm just going to pick the first two functions. So I'm going to add 3x squared plus 4 with x4 minus 3x squared. And when I add them, I'll have x to the 4, then the x squares will cancel out because we have 3 minus 3, and then we'll just have plus 4. Now if I add these functions, go on to Desmos, looks something like this. And this resulting function also has even symmetry. So now I would like you to pause the video, pick another pair of functions 3 more times, and then pick 3 functions to add for the last scenario. Go into Desmos, find that sum of those functions and see what the sketch is going to look like. And then decide, is it even, odd, or neither? And then we can make a little conclusion based on what you notice. So what you should notice when you add 2 or 3 even functions, your combined function will also be even. There we are. Let's repeat the process for our set B functions. So again, just using Desmos, we're gonna sketch these 5 functions, and feel free to pause the video and go into Desmos and check them for yourself. But here is what the first one will roughly look like. The second, linear. The next one will look something like this. The fourth one. And the fifth one. And if we look at all of these have odd symmetry. They're odd functions. So once again, I'm going to pick 2 of these functions. I'm going to add them. I'm just picking the first 2. And I'll collect my like terms here. Here's my combined function. And if we go to Desmos to see what the graph looks like, it's going to look a little something like this. And once again, the combined function has odd symmetry. So now, please pause the video, pick another pair of functions, see what Desmos shows you. Are they odd functions when combined, or even, or neither? And then come back to the video to check our conclusion. So the combined functions will be odd. Okay? And that will always be the case. If you add 2 or 3 odd functions, the combined will also be odd. The next part here, what about subtraction? will this be true for subtracted functions? So again, pick two functions from your even set, your odd set, test it out. So maybe try here 2 even, 2 odd, and see what happens. Then come back to the video to check. And what you should notice is, yes, if you combine or subtract two even functions, the result will be even. If you subtract two odd, the result will be odd. But what about if you take one of each? If you take an even and an odd, what will you have in the end? So once again, please pause the video. Take a function from set A, take a function from set B, add them or subtract them using Desmos, and see what kind of function you end up with. And then come back to the video to check your work. And you should see that when you add or subtract an even with an odd, you will have neither symmetry in the end. Okay. Part 4. Let's go into fancier functions here and repeat the process. So in set A, we have cos x, we have the absolute, we have x to the power of 2/3. And if you graph these functions, you will see that they have even symmetry because they can be reflected over the y-axis. And for set B, we have odd functions like sine x, 1/x, and x to the 1/3. And I want you to repeat the process. So try an example where you add cos x and the absolute value of x. See what Desmos shows you. Is the resultant an even function as well when you have a sinusoidal function with an absolute? Like, will that connection still be the same or not? And then try with some odd functions. Maybe pair up sine x and 1/x. See what happens when you add them. Or in the third one, take an even and an odd. Maybe add cos x and sine x. Do you have any type of symmetry now? All right, so if you take two odd functions, for example, sine x and 1/x, you will still produce an odd function when you add or subtract them. And they look quite funky if you try them on Desmos. If you take two even, you'll still have an even. If you take an even and an odd, you'll have neither. It won't be even, it won't be odd. So, to summarize our findings here, the only function which is both even and odd is f at x equals 0. This function, if I reflect it over the y-axis, it will be the same, or if I reflect over x and y, it'll be the same. The sum or difference of two even functions is even if they're different types of functions, like a polynomial and a sinusoidal, for example. The sum or difference of two odd functions is still odd. And the sum or difference of an odd function and an even function is neither, provided neither function is y equals 0, because y equals 0 can be even or odd. So if you add y equals 0 with any function, an odd or an even, you'll still end up with an odd or an even because y equals 0 works both ways. And that's it for the characteristics of functions, this little add-on. So we looked at what happens if you take the composite function of a function with its inverse. You'll always get x. And a little add-on about adding or subtracting functions. So that's it.